All right, so this is the power output of a hot substance. This is blackbody radiation. Okay, so emissivity is its ability to emit blackbody radiation. So that varies from 0 to 1. Okay, the epsilon naught is our that's our Boltzmann. That's our no wait whose constant is that? I'm forgetting. It is the Stefan Boltzmann constant. There we go, and that is 5.67 times 10 to the minus eighth, and this is watts per meter squared per Kelvin to the minus fourth. Okay, and the concept here is that any object that is not at absolute zero is going to be radiating energy. These are photons of energy. Okay, and the emissivity is just some random number. If they don't give you one, just use 1. This is our constant. This is the area of the object, right? So if it's a sphere, if it's a spherical thing, if it's spherical, right? Remember, it's 4 pi r squared, and you've got that formula. That formula is math formula. Let me find it here. That's math formula 1. Okay, that's M1, baby, is what we'd say, right? Okay, and then this is temperature in kelvins. So kelvins, right? If they give you Celsius, be sure to turn it into kelvins, okay? Anyway, that's what that guy is. Now, understand they often talk about this. So see how intensity is power over area, right? They often take that formula, power divided by area. Well, that's E sigma area, temperature to the fourth divided by area. Well, the area goes away. So the intensity, right, is actually, the intensity is just this, right? This is the watts per square meter coming off of some surface, right? They do that a lot. They like to do that. Okay, so that's what this is, right? Is intensity is power divided by area. And this could also be like we've got 1,306 joules or watts, hitting a square meter, right? And they give you in the constant section, they give you a value for the solar constant, right? So on a bright sunny day, and it's not constant, I'm just going to say, right? On a bright sunny day, there's 1,360 watts per square meter, right? In Oregon, though, in the winter time during the day, it could be like 300 watts per square meter, 200 watts per square meter. It's just like gray. Anyway, remember that's watts per square meter. So that's how bright the sunshine is, right? Okay. And then this is albedo or albedo. I should learn how to say that. So this is total power, scattered power, right? So let's say your albedo is 0.8. These are numbers between 0 and 1. If your albedo is 0.8, that means you're scattering 80% of the radiation, right, over the total incident power. So let's say 100 watts. Our intensity is 100 watts, right? And our albedo is 0.8. Then we are, scattered. Yeah. Okay, so we're scattering, if it's 0.8, then we're scattering 80 watts, and absorbing is scattered, right? And we are absorbing 20 watts. Yeah, it's kind of crazy. So it's almost kind of like the opposite of E, which is sort of weird. Okay, and then this guy is the for blackbody radiation as well. So if we make a graph of intensity versus wavelength, blackbody curves look like this. They're kind of, right? And they have a peak, they have a maximum, a lambda that is a maximum intensity, right? That's our lambda max. And if you know the temperature in kelvins, this is the Lavigne Displacement Law. Okay, what it means is that the peak radiation that's coming off of that is inversely proportional to the temperature, right? So the higher the temperature, the shorter the wavelength. This means if you look at a star, right? A star with a really high temperature will be a really short wavelength, which means it's more blue than red, right? If you see a reddish star, right, then it's a much lower temperature, right? It's a smaller temperature. But anyway, that's what that does. That's the relationship between the temperature of the substance and the peak blackbody radiation. All right, thermal energy transfer.